This video looks at operating systems. So operating systems are probably the most important bit of software that you would find in a computer. The reason for that is that no programs can run without an operating system. It's responsible for controlling and communicating with the different hardware devices, and it provides a platform on which different programs can all work. So if you were to run like a word processor without an operating system, nothing would be displayed on the screen, nothing could be sent to the printer, nothing would work at all. And the reason for this is that application software doesn't know how to talk to hardware devices, but an operating system does. So an operating system sits between applications and the hardware and allows both to communicate with each other. So when you print a document, the application talks to the operating system, which then talks to the printer. So the operating system sits between the user's application and the hardware. It enables applications to use the hardware resources. Now the kernel is at the heart, or is the heart, of the operating system, and it's responsible for looking after those most low-level hardware operations. So when we're talking about the operating system talking to the CPU, memory, the devices, it's the kernel that's doing that. It's the kernel that applications make use of when they want to operate the computer's hardware. So we've already seen how operating systems provide an interface for users, allows a user to work with an application, and then we've seen how the operating system will allow an application to talk to the hardware so they can communicate with each other. But there are further services that the operating system provide. Now, an interface. Memory management, so paging, segmentation, and virtual memory. These are all main functions of an operating system, things that it can do. Peripheral management and multitasking, in particular looking at interrupts and interrupt service routine and scheduling. So we'll look at each of these things over the next few slides. But before we do that, we'll just have a look at different types of operating system first of all. Then we'll look at each of the services that the operating system would provide, regardless of the type of operating system. So there are different types of operating system. You've got distributed OS, embedded OS, multitasking, a multi-user operating system, and a real-time operating system. So when it comes to distributed operating system, a distributed operating system sits in front of and controls a host of different computers. So you can think of this one operating system managing multiple computers that are all connected together, perhaps across a LAN or a series of LANs. And by LAN I mean local area network. So this is clearly quite different from the operating system that we're used to, which are just installed on different computers. So they're designed to spread different tasks across a range of computers to make use of their combined processing power. So the operating system coordinates and controls the processing of all of those different computers that are involved. So to a user that's using that operating system, it would look like a single computer. But behind the scenes, it's making use of all of the different hardware, all the different processing power of those different computers to make a really powerful system. Now, an embedded operating system is the kind of operating system that you would have on a single device that just has a small number of jobs to perform. If you think about a DVD player, it's probably not very effective, very efficient to install Windows as its operating system. There'll be thousands and thousands of things that the operating system just wouldn't need to do. So it'd kind of be a waste of space and a waste of resources. So an embedded operating system, like I said, is one that's designed just to carry out a few jobs for a particular device. So devices such as TVs, mobile phones, dishwashers are all devices which will be controlled by an embedded system. So embedded operating systems are a type of operating system which control these embedded systems. So they're likely to be customized for the device on which they're installed. They need to best harness all of the resources that the hardware has in that device to make sure that it's optimized for the best performance. So like I said before, you wouldn't want to install a Windows operating system onto a small device which just does a couple of tasks. What would be best would be to actually write that operating system so that it uses the resources most efficiently, can run really, really quickly, and therefore make sure that that particular device is optimized. A multitasking operating system. So these are the ones that you would be using on your laptop or on your desktop. So a home PC is likely to have multiple programs open at the same time, and therefore millions and millions of processes all needed to be executed from different programs in pretty much the same space of time. And because these PCs have a limited number of cores, CPU cores, it might only have one core, it might have 4 cores, depending on the CPU you've got. They're not going to be able to execute all of these different processes all at the same time. So instead, what they're going to do is they're going to be executed in quick succession. So imagine a single core CPU. It can only fetch, decode, and execute an instruction one at a time. Now, if you've got millions of processes from lots of different programs that are open at the same time, a multitasking operating system will allow the CPU to be given one job from each program at once, so that each program can take it in turn to have their tasks processed. So a multitasking operating system is specifically designed to enable the management of the processes from lots of different programs, so the CPU can be given the right task at the right time to make it appear to the user that all the programs are running quickly and simultaneously. But really, it's the operating system that's just feeding the CPU with the right processes at the right time to create that illusion. Now, multi-user operating system. This is one where it's been designed so that lots of different users can all access the system resources at the same time. Now, don't get this confused with an operating system that you might have on your home PC. You might have different accounts for different members, and therefore think that that's a multi-user operating system. It's not. The specific difference here is that it's about allowing more than one person to be actually logged in at once and using the system resources at the same time. So these specialized operating systems are likely to be found on mainframe computers. Okay, a real-time operating system. So a real-time operating system is one where it is time critical. So they're specifically designed to perform tasks within a definitive time period. So if you think about a system that controls a nuclear power station, any issues that are detected have got to be responded to immediately to ensure that the system continues to run safely. Imagine computer system in intensive care unit. If a patient has trouble, then the system would need to kick in immediately, warn the doctors, nurses, perhaps automate some breathing equipment to be used immediately for that particular patient. So any operating system where time is critical, it would require it to be a real-time operating system. So aeroplane systems, they need to respond to events such as turbulence within a fraction of a second to ensure the safety of a flight. Again, a real-time operating system would allow this to happen. Okay, they're optimized to process priority jobs really quickly. So they'll also have fail-safe features, so that if a piece of hardware failed, there's another one that can be quickly used. So they need to be incredibly robust because they're used in such time-precious situations. Okay, functions of an operating system. So we mentioned this earlier. We said that operating systems provide an interface, memory management, peripheral management, and multitasking. So we'll have a look at each of these things in a bit more detail now. So memory management. When a program is loaded, it's loaded onto the RAM. And it's the operating system's job to ensure that no two programs can access each other's data, because this could cause issues. It could allow for malicious attacks on data and so on. So another role is to ensure that the free space on the RAM is used efficiently as well. So it's not just about making sure that two programs can't access each other's data, it's also to make sure that when programs are loaded onto the RAM that they are done so using that space as efficiently as possible. So if you think of three programs of different size being loaded onto the RAM, that bar there represents the RAM. You've got program 1, program 2, program 3, and then you've got some free space. And if program 1 closed, then we'd have free space in two different places. And if we wanted to open another program that was slightly too big for both of those spaces, then what would happen? Well, it's the operating system's job to ensure that the programs can be loaded onto the RAM, even if there's no what's known as contiguous spaces available. That means spaces that are physically next to each other in the RAM. So it might split that program up into two parts and fill the holes that way. Now, the two ways that can happen is using a method called paging and a method called segmentation. Now, paging is where an operating system will split a program up into equal sized blocks of data. There might just be a few kilobytes in size, but they're equal in size. So this can then be assigned to non-contiguous memory locations, and this system requires a paging table so that wherever these blocks of data are actually stored, a table will keep track of that, so that if the data needs to be accessed, it can look in the paging table to see whereabouts that data is and access it when it's needed. Now, segmentation is slightly different. Again, programs are split up, but not into equal size. They are split up into logical sizes. In other words, into maybe the modules or the functions of the program. Now, virtual memory, we talked about in the last video. Virtual memory comes into play when the RAM is full. So sometimes, no matter how well the operating system uses paging or segmentation to manage the free space, the RAM can get used up. And another role of the operating system is to manage that situation. And it does that using something called virtual memory. So it's secondary storage, usually the hard disk, being used as RAM. So the programs that haven't been used for a while but are still open, they are regarded as perhaps lower priority to the user, and they're moved to virtual memory to free up some space in the RAM so that new programs can then be opened. Now, the issue with virtual memory is that secondary storage is much slower at communicating with the CPU, so the user will see a notable dip in performance when virtual memory is in use. But the idea is that data is swapped out of RAM and put into virtual memory, and when that program needs to be used, it's swapped out of virtual memory and put back into RAM. Okay, interrupts and the interrupt service routine. So we've heard already that the CPU is a brilliant multitasker. It can carry out the processes of lots of different programs in quick succession, making it appear to the user that all of these processes are happening simultaneously. But there are going to be times when the CPU will have to stop processing an instruction and deal with new requests. So it might be that the user double clicks on a mouse and needs something performed quickly by the computer. So these requests are known as interrupts. So the CPU is interrupted. It needs to deal with that request before continuing with its processing of running programs. And if you think back at the real-time operating system, almost certainly interrupts are going to be very important there. An operating system might be running fine, but then something that is time critical is requested. So the CPU will have to be interrupted to allow that process to be carried out before carrying on with what it was doing before. So when an interrupt is received, the CPU will carry out what's known as an interrupt service routine, an ISR. Now, the ISR will evaluate how important that interrupt is, and it will either add it to a queue. So if it's not that important, it might be added to a queue and be dealt with later on, or it might be handed straight to the CPU to be processed straight away, as would be the case with some important request in a real-time operating system. So when multiple programs are running on a system, it is the job of an operating system to ensure that all the programs are able to run at the same time, or run simultaneously. The operating system does this by managing the processes that are given to the CPU. We've heard about this before. And it attempts to fairly share out these jobs of several programs. And it does this using something called a scheduler. And there's different scheduling algorithms that an operating system might make use of. Now, the examples of different scheduling algorithms, you could have a round robin, you could have first come first serve, multi-level feedback queue, shortest job first, or shortest remaining time. Let's have a little look at these now. So a round robin scheduling algorithm, it literally gives each process an equal set amount of time to complete. And if it fails to complete, it goes back to the back of the queue, making way for the next process. So it's given time, okay, a set amount of time to execute. So it's not that it's each program's given an instruction each and it works its way around, but it's about the time given to complete a process. And if it doesn't complete, it goes to the back of the queue. First come, first serve. So this scheduling algorithm will process the first request and then move on to the next process, and then the next and the next. And all processes that are queued up in the order that they arrive, they're dealt with according to their position. So they're all just queued up and executed one after the other. Shortest job first. So this will prioritize jobs that can be executed the quickest. But clearly knowledge of the execution time of these jobs that are queued up would need to be calculated first. So imagine you're wanting to carry out some maintenance jobs on your computer. You might want to move files into folders, delete unwanted documents, uninstall unused programs before running a disk defragmentation job, which might take a really long time to complete. So it's that idea, trying to get these shortest jobs done first of all, before moving on to the longer jobs. Shortest remaining time. So if you've got lots of jobs queued up at any one time, this algorithm will prioritize those with the shortest remaining time to process. So if you think about a chef cooking several meals at once, they may choose to serve those that have the shortest time left to cook, regardless of when those orders came in. So that's the shortest remaining time. And then you've got the multi-level feedback queue. So this algorithm makes use of a range of queues, each queue given different priority. So it might be there's a queue for an input-output request, one for a shortest job, but whatever the queue categories, the algorithm can schedule jobs between the queues to ensure that the CPU is working as efficiently as it possibly can and maximizing the quality experience for the user. Okay, so another job that the operating system does is peripheral management. So when we're talking about peripheral devices, we're talking about sort of devices that are connected to the computer. They're not necessarily actual part of the computer itself, they're connected to it. So its role is to provide an interface between the software and hardware, as one can't talk to each other, and we heard that earlier. So in the case of some audio playing software, the operating system will receive a request from the program, from the application, to pass data onto the speaker. The application can't talk to the speaker, but the operating system can. So the operating system will then communicate with the speaker in order to pass that data on so that the speaker can then produce the sound that the application wanted. So in that way, it's managing the peripheral devices. Buffers and spooling. So all the devices that are connected to the computer are much, much slower than the CPU. And the operating system needs to manage the requests from these devices to use the CPU as efficiently as possible. So if you think about a request to print several documents, maybe the user wants lots of pages printed out, it would be inefficient for the CPU to be just waiting for each printing job to complete before dealing with the next printing job. What it would want to do is just carry on processing loads of other applications so that the computer continues to work quickly. So to overcome this, the operating system will make use of a small piece of secondary storage, and inside that bit of secondary storage will create something known as a buffer. And it enables spooling to occur. So think of a buffer as a queue, if you like. So spooling comes from the term simultaneous peripheral operations online. Spooling is where peripheral device requests are added to a queue, added to a buffer, with each request then being seen to in turn. So it allows the CPU to be freed up to deal with loads of different requests whilst the peripheral devices are asking for particular jobs to be done, or whilst actually carrying out those jobs. Okay, so device drivers. So if you think about a program or an operating system, operating systems are to be run on thousands of different configurations of computers. One computer might have one sort of CPU, another computer might have another sort of CPU, one might have a certain bit of RAM made by one company, and another might have a bit of RAM made by a different company. All of these different configurations will mean that it would be, an operating system has to be able to talk to all of these different devices, these different configurations of computer, but you can only really write one operating system. So it would be impractical for programs to write an operating system that can communicate with every single possible peripheral device, as there's so many different types and makes. So to get around it, programmers of an operating system will write an operating system, but at that point they may not be able to talk to every single device, every single configuration of device that a computer might have. So what each peripheral device will have is a small bit of software known as a device driver. And this file, this tiny little file, has all the information that an operating system needs to be able to communicate with the device. So in that way, if an operating system, if there's a new peripheral device attached to the computer and the operating system has never heard of this manufacturer before, it'll be able to use the device driver to be able to communicate with that new peripheral device. So the BIOS. So we've discussed the functions of operating systems. Now the BIOS isn't an operating system. It's not a function of the operating system either. But without one, we wouldn't be able to run an operating system. Now the BIOS stands for Basic Input-Output System. So when you first switch on your computer, the BIOS will run. Okay, and its job is to first check that all the components required for a computer to function are all present and working, and that's known as the power on self-test, POST. After running the POST, the BIOS would load the operating system's kernel from the bootloader, allowing the operating system to run and load on the computer. So the BIOS is what is run when you first switch your computer on, and it just checks that everything's ready for the operating system to load, and then it will load the operating system. Okay, virtual machines. So virtual machines are actually software. Okay, they're not machines. It's just software. It's a program that takes on the function of a physical machine, and it can run an operating system. So virtual machines, they're being used more and more and more because with just one computer, if you were to install this software, you could then create the illusion that there are loads of different computers, each running their own operating systems independently, but obviously with a massively reduced cost because you just got the one computer, the one physical computer. So the components of just one computer being utilized to produce the experience of several computer systems. Now, virtual machines are really advantageous as well when it comes to the portability of programs. So we know that a program from GCSE, we know that a program needs to be fully translated into machine code in order for a CPU to run the program. Now, when you translate a program into machine code, the translator will look to see what the hardware is, and it will translate it into machine codes to make sure that the CPU can definitely run that program. Now, an alternative, instead of actually compiling it into zeros and ones, you could, as again we learnt from GCSE, is you could run the source code with an interpreter. So the interpreter will read each line of code, execute it, read another line of code, execute it. But this reveals the code, and the programs run much slower. So virtual machines provide another option, another way to translate and run programs, because they can execute something known as intermediate code. Now, intermediate code isn't source code, so it's not code like Python or C++, and it's not machine code, it's not zeros and ones. It's kind of in between. It's been partially translated. And it is far more efficiently packaged version of source code, basically. It's known as bytecode. Now, because it's bytecode, it cannot be read like source code, so the programming code is secure, but it still needs a little bit more translation to actually be able to run on a computer. So usually programs, they come fully compiled, and it will be compiled so it can be run on a certain type of CPU. But because bytecode is only at this stage partially translated, before the code is run, virtual machines can actually first check the computer's hardware and then decide how to finish off that translation. So it's kind of like half translated, virtual machine has a look at this bytecode, has a look at the hardware that is running on the computer and goes, okay, I know now how to translate this bytecode so that it can be executed by this particular computer's hardware. And because of that, bytecode is really portable. It means that you can just have a program that's been translated into bytecode. It doesn't matter what computer you're on. If a virtual machine is installed, it will be able to look at the configuration of that computer, it'll be able to look at the hardware, and it will be able to then decide how it can finish off that translation so that the program can run on that particular machine. So bytecode is really portable, and we'll look at bytecode a little bit more in a future video.